All right, guys, we can give it another minute or so. I can see some people were still trying to drop in and have their audio connect and whatnot. Got quite an array of folks here. This is very exciting. Let's see. Oh, there they are. More folks. So we'll give it another minute or so for the last folks to join. A minute always feels like eternity when you're waiting for that clock to roll over. Okay. So it is 2:01. I'm sure some people will continue to drop in, but we will get started. So my name is Blair Blanchette. I am the Virginia Conservation Assistance Program Coordinator. And we have Rachel here as well, our Assistant Coordinator. So we're very grateful to have Dan Schwartz of Northern Virginia Soil and Water Conservation District to give an overview of soil science and some identifying features of seasonal high water tables, a couple other things. This has been a topic that has come up a lot. We've gotten a lot of questions about VCAP practices, where they can be cited for, who is responsible for making these determinations. This is going to be an ongoing series of, or rather it's going to be an ongoing process of learning about these topics, learning about citing for these practices. So this is kind of step one of supporting districts in learning more about VCAP, about the practices that we offer, and where they should go. So I don't want to take any more time away from Dan. Dan will give his presentation. We'll have some time for questions. And then the last thing I want to say, actually, before I turn it over, is coming July 1 is the start of the new program year, of course, for VAX, but also for VCAP. So we will be releasing a new manual. We will have a manual update webinar on July 2nd. Every Tuesday before applications are due, we have a water cooler chat where you can ask questions. It can be about things like what Dan's going to talk about. It can be about the new manual, site inspections, applications, or different site visit requests that you've received. So I'll kind of reiterate that at the end of the webinar, but I want to turn it over to Dan to start his presentation.
Great. Thank you very much, Blair. Good to see a good number of people interested in this topic. I know it can be kind of a stressful one when you're trying to design a rain garden, a dry well, whatever it may be, and you're not exactly sure where that seasonal high water table can be. Hopefully I will give you some insight into how you can get a pretty good guess of where the seasonal high water table is, but there's sometimes you don't want to make that call yourself. If you have to call an expert in, call an expert in. If you need to tell your client to hire a soil scientist to come out and check out the property, that's perfectly fine. And that gives you some peace of mind and some protection as well, too. I don't know too much about who is out there in the local county agencies as well, too, that might be able to help. I know our health department and probably most of the health departments in counties throughout the state have, if not soil scientists, people on board who are really good at determining seasonal high water table, because they have to do that for septic siting. And maybe, if you have a good relationship with them, perhaps you could get them to come out and take a look at the site for you for free. You can also pick at your NRCS contacts as well, too. NRCS does have resource soil scientists posted in different parts of the state. Generally, there's one of them for several counties, so they're pretty busy, but perhaps you could get them to come out and look at some of your VCAP sites as well, too, and get that professional eye on it. So don't always feel that it just has to be you making this decision. But if for whatever reason you feel like you can make the decision, or there's no other options out there that really would work, I'm hoping this presentation will at least give you a little bit more knowledge that you can use to increase your confidence in what you're doing. Let me share my screen. Got a little PowerPoint that I put together. Hopefully everybody can see that. Oops, I'm on the last slide. Oops. Sorry about that. Started on the wrong end. Determining season high water tables. So, sometimes, and this is the best case scenario, sometimes finding the water table is so easy. If you have a situation like this where you're digging a hole and that hole fills up with water, that's all you need. That's all the proof you need. Unless there's a burst water pipe somewhere nearby, which is a bigger problem, you found the water table. You can stop digging at this point. If you're finding that water flowing into your hole from the sides and bottom, 6 inches, 10 inches, whatever below the surface, there's no way you're going to be able to put a rain garden, a dry well, even porous, permeable paving here. Because with the VCAP standards, you have to have 2 feet of dry soil that separates you, the bottom of your rain garden, your dry well, whatever it might be, from the top of the water table. Obviously, in something like this, you just can't do it. So that's nice. If you can find this, well, it's not nice, obviously. If you have a nice client who's really looking to put in a rain garden, and this is what you find in their backyard, there's not going to be a rain garden for them. Maybe a constructed wetland, but not a rain garden in this case. The problem is it's usually not this obvious. And even in soils, when it is obvious, it's not always obvious when you are digging at that soil. So I found this data to be really interesting. So I live in Fairfax County near Reston. And in Reston, there is the U.S. Geological Survey headquarters. And behind their office building, they have a groundwater monitoring well. There's not too many of these monitoring wells throughout the country or throughout the state. There's probably, I shouldn't say that. There's probably 15 or 20 spread around the state. But there's not a lot of long-term monitoring, at least in this part of the world, of groundwater levels. But luckily, just down the street from me, there is this monitoring well that's been going since, I think, the late 70s. So I just went and looked at their data a little while ago and averaged the daily average depth, the monthly average depth to the groundwater table over the last 22 years, from 2000 to 2022. And this is what I found. So it kind of creates this, I guess you call it a sine or a cosine wave. It's been a while since I took my trigonometry. But the interesting thing is, you look, let's say January, the average depth there over the last 22 years was 13.6 feet from the surface to the surface, from the ground surface to the surface of the water table. We get to April, it's quite a bit shallower, 11.62 feet. And then we get into the warmer periods. That groundwater drops until it bottoms out in October at 15.64 feet. So 11.6 feet, 15.6 feet. We've got a 4-foot drop over average over the last 22 years. And I think if you are able to find a monitoring well in the USGS network, and they are out there, if you can find the right websites, you'll probably see, at least in this part of the world, a very similar pattern. You go somewhere where the climate's totally different, like California or Alaska, you might see something different. But at least on our East Coast temperate climates, this is what you're likely to find when it comes to groundwater. So that's why we say we're looking for the seasonal high groundwater table, because there's certain seasons when the groundwater peaks, and there's other seasons when the groundwater has really receded. And in fact, if you look at the dates where it peaks, April, and the dates where it bottoms out, October, it begins to make sense. It really is dependent on the growing season. So what's happening in April? April is basically the end of dormancy for plants. That's when the first leaves start to come on your trees, shrubs, things like that, except for those very early, flowers that we see coming out in February and March. But for the majority of our plants, they're really beginning to bud out in April. And when the leaves come back on the trees, it means that the trees, the shrubs, the other plants are now active. They're coming out of dormancy, and they're beginning to take up water through their roots. And roots are basically just like big soda straws poking down into the ground. They're extracting oxygen and they're extracting water. So when the plants are active, all those roots are slurping up that groundwater. And what happens? The groundwater recedes as a result, just like sticking a straw into a glass full of Coke. You take a big sip of it, what happens? You get some of the Coke, and the level of Coke in your glass drops. And that's what's happening from April all the way to about late October. Late October is when, the leaves really start falling off the trees, meaning fall is coming, and the trees and plants are beginning to go back into dormancy. But they've had all those preceding months, April, May, June, July, August, and September, where they were active and they were drawing down the water table. Now you get to October, they start going into dormancy, and you start to see the groundwater slowly begin to inch its way back towards the surface. So if you're looking for a date, and it's going to change from time to time, obviously, these are averages. If you get a really big rainfall or a very wet March, you might find your peak in March rather than April. But generally speaking, early April, I'd say April Fools is about the time you'd expect to find the groundwater highest, and Halloween is about the time you'd expect the groundwater at its lowest. But this brings up the problem. So let's say you were in a really wet soil, but you happen to be digging your sample in October 30th. Well, in this soil, maybe we go down 11.5 feet. It's going to look perfectly dry. We go down another 4 feet and it's still going to be dry. But we're not going to be able to tell from that sample alone where the water table rises up to at its lowest point. And that's really what we are interested in. What is that high point? What is that early April high point where the water table comes closest to the surface? It's great if we can get a rain garden, but we want that rain garden functioning throughout the year, not just for 6, 7, 8 months. And then the other 4 months, it's inundated from the bottom with rising groundwater. That would be an unhappy client, most likely. So it is important when you dig. What this means, though, is that if you're not digging during one of those wet periods of the year, you might be missing groundwater if the only thing you're looking for is whether that hole that you just dug fills up with water. In April, it will. In July, August, September, October, it probably isn't. Even in November and December, it may not as well. So you need some additional data to help you make the decision of where that groundwater actually is. And I think one of the easiest ones, since it doesn't require any expertise, is to check the soil survey first. Some of you might be in a county where they have their soil maps on the county's GIS system or on the county's website where it's available. Most people go to the USDA's Web Soil Survey. That's through the Natural Resources Conservation Service, NRCS. So websoilsurvey.nrcs.usda.gov, that's really a great starting point if you're trying to figure out, just by looking at a client's property, whether it might be suitable for an infiltration practice like a rain garden or dry well or permeable pavement, or whether you should be looking for something else that doesn't rely on good, dry, poor soil. So websoilsurvey.nrcs.usda.gov. What I'm going to try and do here is I have some of the screenshots saved. I think it's always a little bit more useful to actually go to the website itself. So let me stop sharing this and let me see if I can pull up the website and make it visible to all of you as well. Oops. Oh, I'm not doing that right. Hold on one more second. Let me see if I can get it now. There. Hopefully you can see if, as I'm clicking through, I know sometimes when you click from one web page to another, sometimes it stops sharing. So if the screen freezes, please let me know, Blair. So basically, when you get to the Web Soil Survey, this is the landing page, and it's got this nice big green button here that says Start WSS. That's what you're going to want to click. I was already in a session, so I need to start a new one. And if you never used it first, what you can do is on this bar over here, on the navigation page over here, you can navigate by address, you can navigate by state and county, excuse me, by soil survey area. Usually it's easiest just to do address. So I'm going to just put in my own address. And it'll zoom in for you. And the next thing, once you've zoomed into the general area that you were looking for, you have to create what's called an area of interest. These little buttons up here, AOI, area of interest. Basically, that's just saying, I'm going to draw a box in this case on the landscape surface, and I want soil map information for the land that falls within that box. So I'll do that right here. All right, now I've got my area of interest. And once you have your area of interest, you can see it by the hash marks right there. It makes all the other data tabs up here active. The first one you want to click in is the soils map. So this will actually show you the soil survey map. So each of these little yellow, orangey lines here is a different soil type mapped across the landscape. And then here on the left-hand side, you can see a brief summary of all those soil types that we have, at least within the area of interest. But really, what's more important for this topic is the next tab, which is the Soil Data Explorer. So we'll click on that, and that's where you really get into the suitability data, sort of the more tabular data and the numerical data that describes each of these soil types. So it's great to have the map, but what does that map mean? It's an alphanumeric code. What's 30A? What's 93B? Well, it's not all that important right now, but because what you're looking for specifically is how wet or dry are these soils. And there's a lot of ways to do this, but the most obvious one is to click on the Soil Data Explorer. When you do that, it opens up all these new tabs. One of the most important ones is Soil Properties and Qualities. I'm going to click on that. Brings up a new drop-down menu. The bottom option is Water Features. I'll click that open. And there, the first option underneath Water Features is Depth to the Water Table. You can play around with how you want to report it, but I won't get into those details right now. Instead, we'll just click on the View Rating. And it's nice because it brings up a color-coded map. You can click on the Legend button up here to see what those colors mean. Basically, each of those colors signifies a different depth to the water table. So the redder we get, the wetter the soil is. So red would be 0 to 25. We don't have any red soils here, but we do have some orange ones. I know this happens to be in centimeters. So these orange soils are showing pretty wet soils with a seasonal high water table of 25 to 50 centimeters below the surface. Take those centimeters, multiply them by about 0.4, and you get your inches. So this is saying anywhere from about 10 to 20 inches we can expect to find water table in these orange soils. And then on the yellow ones, it's 50 to 100 inches. So that's about, 50 to 100 centimeters. So that's about 20 to 40 inches. And then the rest are the dark blue, which means we're not expecting to find any water table within 200 centimeters. So basically within 40 inches or so, you're really not going to find anything. That's a pretty well-drained soil. You don't have to just look at the numbers. You can scroll down and it actually gives you the numerical data. So here's the rating in centimeters. So let's say that wettest soil that we have is probably this one, 30A, Cadorus and Hatboro soils, 0 to 2% slopes, occasionally flooded. You can probably tell just by the name that this is not a great soil for a rain garden. But if you want even more data to back that hunch up, just go over to the ratings table. There's your centimeters, average depth to the water table, 38 centimeters. So again, about 15 inches or so. Look at the next one, though. Glen Elk Silt Loam, 2 to 7% slopes, which is often found right next to Cadorus and Hatboro soils. We're not expecting to find any groundwater within 200 centimeters of the soil surface. So that could be a potentially good spot for a infiltration practice. There's more data in the Web Soil Survey, a lot more data. Some of it's very useful if you're looking to see if a soil can perk, basically, if it's dry enough, if it can drain. There are ratings tables just like this one for depth to bedrock, for a depth to a restrictive layer, and a restrictive layer is just a general term for any layer that makes water passage difficult. This could be a naturally dense layer, it could be bedrock, it could be a frozen layer. We're not going to find that around here, but if you were in a colder part of the world, you would. There's also septic ratings. Generally, a soil that's poorly rated for septic is going to be poorly rated for rain gardens and dry wells. And actually, I didn't realize this. They keep adding new data. They do have a suitability for infiltration practices rating now too. And I'm forgetting where that was. It might be suitabilities and limitations for use. Is it land management? There's so much in here, unfortunately, that sometimes you find a cool data point and you forgot where it was. But there is an actual rating for shallow infiltration, things like rain gardens and dry wells. And that's a very useful one for you as well, too. And that's a little broader than just groundwater, because obviously a soil can be limited for rain gardens if it has that shallow bedrock, if it's very clay and just doesn't perk well, or for a variety of other reasons. So if you're looking for a more holistic rating to determine if a rain garden, dry well, permeable paving, or whatever will work, that's a really good one. So just click around until you find that one. It's in one of these two big categories, suitabilities and limitations, or soil properties and qualities. Unfortunately, I'm forgetting which one it is right now. But this is a really good resource to start poking around. And oftentimes it's the only resource you need to determine if a site is suitable for your infiltration practice. Like I said, there's other ratings on there. If you find, let's say you have a soil that Web Soil Survey says it's likely to have a shallow groundwater, but you were out at the site and it looked pretty dry. We can poke around and look at other things as well too. There are hydric ratings. Hydric ratings are basically wetland soil ratings. If a soil is rated as hydric, you're almost certainly not going to be able to get a rain garden installed there. So if you find high groundwater ratings and hydric ratings, then chances are it's not a good site. But even with this, there's still some uncertainty because these are general maps. And I know how general these are because this is one of the maps I helped create. I was on the team that helped make the soil survey maps for Fairfax County. I'd say the Fairfax County maps are probably even a little more general than most soil surveys just because it's such a built up urbanized county. So there's a lot of areas we just had to rate as what we call urban land, meaning it's been paved over. There's just a lot of areas where there's not a lot of access. So there's guesswork that goes into making these maps. And even in a perfectly constructed map, soil is a continuum. So within pockets of bad soil, you're going to find little pockets of good soil. Within big areas of good soil, you're going to find little pockets of bad soil as well too. So just because a soil is poorly rated for infiltration does not mean 100% of the time that you can't get a rain garden to work there. Sometimes it'll tell you with enough certainty that you just probably shouldn't try it. The odds are stacked against you. But sometimes if what you're seeing out in the site is really different than what you see ratings-wise on the Web Soil Survey, the soil survey maps, perhaps that's one of those soils where you've got that little pocket of good, well-draining, drier soil than the soil maps would actually indicate. But either way, whatever you end up doing, I think this is probably the place where you want to start. Go to the Web Soil Survey or your county soil survey maps if they have their own mapping service, and just check out what those ratings are, specifically depth to the water table. And then you can look at a few other things as well too. Hydric soil ratings, infiltration ratings, depth to bedrock, depth to soil restrictive features. It's worthwhile poking around in the Web Soil Survey for about an hour to see what kind of features they have. And it's really these two big categories, the suitabilities and limitations for use tab and the soil properties and qualities tab, where you're going to find most of that useful information. And that's all under the even bigger tab, the Soil Data Explorer. Pull up your soils map, and once you do, the Soil Data Explorer will become active, and you can start poking through all the data that's stored in there, which is voluminous, more than you'll ever need. I'm going to stop sharing here, go back to my, shoot, where'd it go? Hold on, got to chase down my PowerPoint now. There it is. All right. So you can ignore these slides because this is just what we looked at. So let's say you've looked through the Web Soil Survey and you're not entirely convinced one way or the other that yes, it's possible, or no, it's impossible to put a rain garden in here. Well, at that point, you do have to go out and start looking at the soil and seeing the details in place, the characteristics in place. So it's time to grab the shovel, grab the soil sampler, grab the auger, whatever it is that you're going to use to dig, and go out to the client's front yard, backyard, or field, or whatever it is. And this is where you start using something called soil morphology. Again, if you're digging in one of those times throughout the year where the groundwater might be a little bit lower and it's not going to just simply fill up the hole as you're digging it, you have to start looking at the colors and the features of the soil, what we call the morphology of the soil. And really what we're looking at when it comes to morphology and determining wetness is iron and manganese. These two minerals, because of the colors they produce when they're wet versus when they're dry, can really give us a very good clue as to where the seasonal high water table is, even if the soil at the time that we're examining it is dry. So this is your classic red Virginia clay. And this is a very good example of a soil that's very, very dry. And it's because it's full of iron oxide. Iron oxide is basically just rust, natural rust. You leave your bike out in the rain, it rusts. You leave your soil out in the rain, it rusts as well too. As the rainwater percolates down through the soil, it brings with it some dissolved oxygen. That dissolved oxygen interacts with the iron in the soil minerals, in the bedrock that as it's weathering, in the sediment as it's weathering, and it creates iron oxide, rusty red colors. It can also be yellow. It can also be, kind of a straight brown as well too. It's usually somewhat of a combination of the three. So if you're looking at a soil that's pretty much completely reddish, yellowish, or red, yellow, brown from top to bottom, you're most likely looking at a very dry soil. This is actually saprolite, meaning a rock that's beginning to break down. Those black streaks that you see in there, that's the manganese oxide. So when manganese interacts with oxygen, it creates jet black, almost like a coal black color. I hope you can see my cursor, but there's a nice little manganese oxide streak right there. And there's another manganese oxide streak, kind of an eye-shaped one. Looks like that big storm on Jupiter a little bit. But manganese oxide, nice, dark, very dark brown, but usually jet black. Iron oxides, reddish, yellowish, brownish. So really, when we think of red Virginia clay, it's actually not the clay that's red, it's the iron oxide coating on the clay. That is the red color. Oops, there's that manganese oxide. Now, most sand, silt, and clay grains, what we call their naked color, meaning if they have no staining on them from either iron, manganese, or the other things in soil that can give you color like organic matter, the naked mineral color of most sand, silt, and clay is actually gray. So here in the middle there, that's kind of what your typical Virginia sand, Virginia silt, or Virginia clay would look like if it had nothing staining it. It would just be sort of a dull gray color. Some of them are a little darker gray, some of them are a little lighter gray, but generally it's just gray. What we have here on the outside, that's the iron oxide staining, the red right here and the orange colors, and some browns mixed in there as well too. So without that staining from iron, from manganese, or from a few other things like organic matter, most soil is just going to be straight gray in color. Now, this is important for us because the colors that we see in soil are very indicative of the saturation level of that soil, at least sometime throughout the year. Generally speaking, iron oxide, well, not generally speaking, always speaking, iron oxide and manganese oxide exist in oxygenated environments. They need oxygen in order to combine and create the iron oxide or manganese oxide. So what happens to those iron oxides and manganese oxides when they're living in a not a saturated anaerobic environment, meaning an environment where the oxygen in the soil has been depleted? Well, generally speaking, if a soil is saturated for about 2 weeks or longer, and there's biological activity in the soil, meaning there's microbes or other critters that are decomposing organic matter and using up the oxygen, after 2 weeks of that saturation, the free oxygen within that soil is going to be pretty much entirely depleted, and you're going to have an anaerobic, anoxic type of environment. At that point, those critters, those microbes, start looking around for other sources of oxygen. What do they look for? Well, they can use the oxygen that's in the iron oxide. They can use the oxygen that's in the manganese oxide. So they actually kind of break off the oxygen. They use that, and it causes the iron and the manganese to reduce. And when iron and manganese reduces, meaning it loses its oxygen, it goes into an electron gaining state. Both can become soluble, and they can become invisible as well too. So basically, especially with iron, reduced iron is dissolved iron. That reduced iron, once it's no longer iron oxide, it becomes reduced. It's gained electrons. It's lost its oxygen. It dissolves in the water, and it loses that red color. Sometimes it dissolves and washes away, and then this whole soil loses its red color. Sometimes it's dissolved, but it still stays there, but it's a clear color. It's not staining the soil that red anymore. Same thing happens with manganese oxide too. It dissolves, and oftentimes it'll wash away. And if they can find another spot in the soil, another little kind of unique habitat in the soil that still has some oxygen left in. That water with the dissolved iron and the dissolved manganese, as it diffuses into that oxygenated pocket of soil, it will reform as iron oxide and manganese oxide, and those red and black colors will reappear. So that's very important. When they dissolve in saturated anaerobic conditions, they become invisible. And when they reform or reprecipitate in oxygenized pockets of soil, the red color of the iron oxide and the black color of the manganese oxide returns. And this, over time, creates your classic, what we call redox modeling color pattern. So what we're seeing here, and all those little spots in the soil that are marked as C, those are iron concentrations. Those are basically little pockets of soil that, for whatever reason, never got fully anaerobic. They always had some free oxygen there. And those areas marked D are areas of the soil that were reduced. They did become anaerobic, and the iron oxide dissolved. As that iron oxide dissolved, it flows out with the water as the water flows through the pores of the soil. And if it happens to hit one of those little oxygenated pockets, that iron oxide reforms. So you've got kind of the grays mixed with your oranges and reds in this sort of almost like a modeling pattern. It's almost like the coat of a dog in some cases, if you've seen some of those. I'm forgetting what that color pattern is, but a brindle, I guess you would say, brindle dogs that have this kind of odd splotching pattern on it. So the splotchiness is a very good sign of seasonal high water table. You could be digging through this soil right here, and it could be perfectly dry in the middle of July, August, September. But if you see these colors, that's a very good indicator that at some point throughout the year, this soil is really, really wet, and wet for a long period of time. So generally, like I said, it takes at least 2 weeks of consistent saturation to reduce or use up all of the oxygen in the soil and create the anaerobic conditions necessary to dissolve and reduce iron and manganese. But generally speaking, the longer those reduced conditions occur, the more grays that you will see in the soil. So if you just see a little speckle of gray here and there, that might be a soil that's wet for 2, 3, or 4 weeks. If you see a soil that's half gray, half orange and red, that soil might be reduced for 3 or 4 months. If you see a soil that's pretty much all gray and there's maybe just a few speckles of orange and red, that might be a soil that's saturated for 9, 10, 11, or even 12 months out of the year. So it's really the proportion that kind of determines how wet and for how long that soil is. This soil here, it's a pretty wet soil. Lots of grays in there that you can see. Now, not all grays are created equal. To count, generally, there's always exceptions to the rule, but the general rule is you have to use your Munsell soil color book to determine if the grays in your soil are really indicative of wetness. And for your average Munsell soil color page, like this 10YR page over here, hopefully that's big enough for you to see. If you're not familiar with Munsell soil color books, each page has this alphanumeric code 10YR. That's called the hue. Basically, it means the general color. In this case, 10YR means all the colors on this page are a mix of yellow and red mushed together. Then you have your value, which is the number on the rows over here. And then you have your chroma, which is the number at the bottom. Value is basically the lightness or darkness of the color. You can see as we go from top to bottom, we get very light colors, and they get consistently darker as you drop down towards the bottom of the page. And then chroma is the intensity of the color. It's almost like you start with a very plain, bland gray, and you start adding more and more and more pigment. That's what chroma is. It's like more and more and more pigment. So as you go from left to right across the screen, you'll see that the soil color chips go from very gray to a much more vibrant yellow-red type of color. It's not so important to know all those things. What really is important for this case, if you have a Munsell soil color book, and you really do need one of these if you're going to try and determine seasonal high water table out in the field. The gray colors that are used as an indicator of wetness are those that have a value of 4 or higher. So basically, it means from this column on up, plus a chroma of 2 or less. That means from this column, oops, sorry about that, this column to the right. So basically, these chips that are isolated by this checked box right here, those are the ones that have that gray color, which is typically indicative of iron reduction and iron reduction is indicative of saturation. Now, there are a few special pages at the very end of the Munsell soil color book called the Gley pages. The Gley pages are basically all gray. And you see that it's a very different kind of soil color pattern over here, sort of a greenish gray. There's another Gley page that's more of a blue gray. For the Gley pages, those are often the pages that you use for wetland soils, really, really wet soils, and also those kind of odd, weird soils that just happen to have a blue or a green parent material, meaning like a glauconite sand or something. They formed from a mineral that naturally has a blue or a green color, so it can get a little confusing there. But the Gley pages are even a little simpler. Basically, anything with a value of 4 or higher on the Gley pages, you can ignore that stuff about the chroma 2 or less. Just say 4 or higher. So basically, everything from this row on up is considered a color that is indicative of reduced iron and therefore seasonal high water table. So on the most pages within the soil color book, it's got to be a value of 4 or higher and a chroma or 2 or less. On those 2 special Gley pages at the very end of the Munsell soil color book, you just need a value of 4 or higher. So a lot of times, if you talk to a soil scientist or the folks who work for septic companies, they'll say something about chroma 2 models, and that's what they're really referring to. That's just shorthand for this. Models that have that gray color that are 4 or higher or chroma 2 or less. Now, as with everything, and especially with soil, there are complications. We always try and put these neat boundaries and rules on Mother Nature, and Mother Nature always says, well, no, there's these examples that don't quite fit. So there's plenty of times where you're going to find gray colors that might even have that value of 4 or higher and chroma of 2 or less that are actually not indicators of redox, not indicators of wetness. And that's where it gets really complicated. So this is probably the hardest thing to do. I get tripped up with this. It's one of those things where it's like practice makes you better. So the more you do it, the better you are. I don't get out in the field as much as I used to. I can feel my skills slipping a little bit, and I get confused by these odd colors that look like they should be indicators of wetness, but are indicators of something else. So this one, for instance, this nice, almost perfectly rectangular shaped model in here, and you see a few other ones as well. Is that redox? I bet if we colored it with the Munsell soil color book, we'd have a value of 4 or higher and a chroma 2 or less. This is actually not redox. This is something called lithochromic. Litho being short for rock, chromic being color. Basically, this is a gray color that was inherited from the rock. So this soil formed from, I'm not sure what type of rock that is, but just a naturally light colored rock. Maybe it wasn't originally light colored, but as it weathers, it becomes very light, chalky white in color. But not because it's wet, just because that's what that rock looks like as it starts to break down into soil. How can you tell? That's where the art comes in. We'll go over this a little bit more on some of the other pages with some of the other photos that we have. But generally, if you have a lithochromic color, the very sharp boundaries. You can see this goes almost immediately from pure white to this very, very rusty red Virginia clay type of color. You generally wouldn't see that real quick, sharp boundary on a redoxymorphic model, meaning a color that was caused by iron reduction. It's usually a much more diffuse boundary when it's caused by iron reduction. So really sharp boundaries, you're probably looking at something that's lithochromic, a color that's inherited from the weathering rock. What about this one? Even tougher. Is this redox? In this case, no. This is what we call a relict feature. Relict means indicative of something that was going on in the past. Think of relic. A relict feature means this soil was wet at some point, but it's not now. And again, the reasons are kind of the same. This one's even tougher to see. It's harder to show in a picture as well too versus something in the field. But this one's tough. Basically, again, it's that really sharp, diffuse boundary. It's not true in all cases, but if you look at most of these red colors and look at the gray right next to them, it's an immediate transition. It goes right from red to gray with a very sharp boundary between the two and no diffusion, no what we call halo around them, where it's kind of a grading of the color. Maybe it goes from red to sort of orange to yellowish and then eventually into gray. There is no diffusion here, just very sharp, and goes right from that dark red to that very, very pale gray. So if you're seeing those really sharp boundaries, that might be a relict feature. And it's really sharp boundaries that have nothing to do with chunks of rock that are in the soil right now. So this was probably a soil that was very wet. Maybe it was in a wetland that got drained for agricultural purposes many, many years ago. Maybe it was just naturally in a wetter spot, and over thousands of years, millions of years, plate tectonics and other geologic processes have pushed it up and put it into a drier position. But whatever the cause is, this is a relict feature, meaning it's indicative of past wetness, but not current wetness. So, it brings up this really tough thing. What is redox and what is not? I'm sort of, this is the area where it gets very confusing, because I sort of tell you what to look for and then give you all the examples that meet all those requirements that you're supposed to be looking for, but I'm telling you that that's not actually indicative of water table. So here are some things that you can use to kind of guide you to the right decision, whether that chroma 2 model, that a value 4 or higher and chroma of 2 or less gray splotch in the soil is really indicative of current wetness, or whether it's something else entirely. So what is redox and what is not? It probably is redox if you're seeing that gray splotch around a source of carbon. So where does the oxygen get used up fastest in a wet soil? It gets used up around decomposing carbon. You got a little pore, a channel, a root, a leaf, something that is a really good food source for the microbes in the soil. The area around that decomposing organic matter is going to be using up oxygen more, because it's chock full of microbes, and those microbes are using oxygen to aerobically decompose that organic matter. Another spot where you'll find redox more frequently is around flowing water. So if you're looking through your soils, this won't really work if you're using a soil core or a soil auger, but if you happen to have a big pit of that you can get into and poke around, you can see where the pores are, where the channels are, where the natural aggregates of soil have cracks in them that are allowing rainwater down through. If you're seeing gray colors in those pores, in those aggregates, kind of concentrated along the surfaces of those aggregate faces, that's a very good sign that the gray you're looking at is really indicative of wetness, of seasonal high water table. This picture here is really nice because it shows you right down in the center. We obviously had a root channel. That root was being decomposed by microbes, so they were using up the available oxygen much faster than the areas around. And you get that really nice halo. So remember those sharp edges that we saw with the other colors, the relict and the lithochroma colors? Here, right around the root, where the biological activity is the highest and thus the oxygen usage is highest, you've got this kind of sleeve of gray. And it's probably a couple millimeters in width, but then you get beyond that sleeve, kind of transitions into this light yellow, and that light yellow eventually transitions into that nice red Virginia brick-like red clay color. So that's the halo that we're talking about. So here we're seeing both that diffuse transition, that nice halo type transition where it goes from red to yellow to, from gray to yellow to red. We're also seeing that it's very much centered on a root channel, meaning a source of carbon. And oftentimes root channels themselves are a good pore space for flowing water to pass through to, especially if that root has died. So this is kind of checking off all the boxes for us. If we see this in a soil, you can be very certain that this gray color is really indicative of seasonal high groundwater. Here's another good example. This is a soil that has both relict colors and active seasonal high water table. So here we've got a nice root coming through, and you can see that nice gray sleeve forming around the root. So we kind of cut off the top, and you can see the gray right around the edge, and it's transitioning halo-wise into that yellow and then eventually to the red. If you look down here, it's a little harder to see, but there are some relict colors there, very sharp-edged. You go right from the gray color directly into the red color without any transition, without any halo. And again, it's not really showing this in high detail because it's kind of off in the corner, but there's nothing here in this section of the soil that indicates that there's a lot of organic carbon there. We don't see any obvious roots right around those gray colors, nor do we see any obvious pore spaces that would be a pathway for flowing water through here. So this soil has both relict colors and active gray colors that are indicative of seasonal high water table. And here's a really good picture of the gray halos around roots, or excuse me, around pores. So these pores, they weren't root channels. These were just pores that allowed water to pass down through the soil. They saturate first because they're the pathway for water to get into the soil. They get very, very gray. You can see that halo color. It kind of transitions to this orangey, kind of washed out orangey color around the gray, and then eventually off into that nice dark brick red Virginia clay color. So that's a good example of redox colors forming around flowing water pathways, pores. Now here's a good example of lithochromic color. So if you're digging through the soil and you see this big chunk of gray, you might be very tempted to say that that is seasonal high water table. However, we look over here, got a growing root. What's happening around that growing root? It's red. We don't see any of that halo of gray around the root. We don't see any redox forming around the root. This is where really the first redox would start forming. Those first reduced iron gray colors would start forming. So if there's nothing like that around the root, what it's telling us is that whatever's causing this color, it's probably not wetness. So if you're looking at something and you're not sure if it's really indicating wetness or not, maybe it's relict colors, maybe it's lithochromic colors, look for the nearest root, look for the nearest source of organic carbon and see if it's gray around that carbon as well too. And when it's not, you might have to push yourself towards the belief that this is a gray color that has nothing to do with wetness. So this is probably the best picture of a halo, a redox halo that I have access to. Most of these pictures came from Dr. Galbraith at Virginia Tech. If you know him, he's a really, really great resource. He's the coach of their soil judging team, national champions soil judging team, I should add. So I like to say that redox is heavenly, meaning it's got this nice halo around it. And this is a really good halo. You're not going to see much clearer than this. So this kind of red streak, almost like a vein-like color that you see down here, it's either a pore or a root channel. I'm not sure exactly which one it is. It's oxygenated because there's obviously oxygen that was allowed to get into that channel. It must have been connected to the surface. But then all around it, you see that sleeve of very, very, very pale white gray. And then slowly, as we get further and further away from it, what we find is that we get that halo color where that kind of color that comes from iron oxide starts to slowly seep back in. So again, what this means is this probably was a root channel. The root was growing in it. The root died, became decomposable organic carbon that the microbes started munching on, and they depleted all the oxygen first around that root channel because that's where the biological activity was greatest. As that root channel depleted, the iron oxide dissolved because there was no more dissolved oxygen to keep it in that iron oxide condition. And it slowly diffused out with the water until it hit these more oxygenated pockets a little bit further away from the root. And you can see that nice transitional halo as you move from that almost white gray color around the edge of the root channel to that really brick-like red color, just 2 or 3 centimeters away. And then that beautiful orange, yellow to orange transition in between. If you don't see those diffuse boundaries, if it just goes from gray directly to red, then you might be looking at a relict feature or a lithochromic feature, something that is not indicative of wetness. So there's your relict lithochromic type feature. Sharp boundaries, no halo. The gray colors are definitely chroma 2, meaning the value is 4 or higher, the chroma is 2 or less, but it goes right from that gray color directly to that red color without any of that nice halo like we saw, that transitional halo like we saw here. So it's tough. It's tough to tell these things apart, but hopefully that'll give you some assistance if you're trying to make a call. So sort of the big rules to look for: is the gray color next to oxidizable oxygen? Is it next to, a dead root? Is it next to what even seems like a living root? Is it next to a leaf? Is it next to something that microbes would want to eat? If the answer is yes, that's pushing you towards active redox, active signs of high water table. If not, it might be something else. Does it also occur near area where water is passing through the soil? Is there a channel through the soil that would allow water to percolate down into that area where you're seeing that gray color? Is it along the face of a soil aggregate where water could pour through? Is it along some crack in the soil that allows water to get in there? That's also a good sign, if the gray color is located there, that it is actively forming, a symbol of reduced iron and saturation and wetness. And then lastly, you look for the halo. If you could find that halo around the gray color, that's another really good sign. If you have all three, you can be very confident that what you're looking at is active redox and a sign of seasonal high water table. If you have none of the three, it might be something else. This is where you have to use some judgment too. Look around, use the landscape. Where are you seeing these gray colors? Are you up on top of the hill? Are you down at the bottom of the hill? Are you near a stream? Are you near a floodplain? If you're seeing gray colors and you can see a stream next to you, even if it's not meeting the classic characteristics of redox, it's not necessarily forming around a root. It's not necessarily forming around a pore where water can enter. It doesn't have that clear, visible halo. You're seeing the gray colors and you can see a stream very close to you and you're at similar elevations, it's probably seasonal high water table. Use the web soil survey as well too. There are soils that can be very high up, very far from any stream, very far from any valley at a high elevation that can be wet, because wetness doesn't always come from groundwater rising up. Sometimes it results from, let's say, an impermeable layer like clay or shallow bedrock that doesn't let rainwater percolate down. So if you look on the web soil survey and it says, yes, this soil should be very wet. It's very wet because it's next to a stream, or it's very wet because it's at the top of the hill, but there's this really dense, sticky clay layer at 18 inches and water's just not going to pass through. And at 18 inches, you're seeing these gray colors. That's a pretty good sign, again, that it is active seasonal high water table. And then lastly, use the soil morphology. If you're finding those gray colors next to roots, if you're finding them around oxidizable organic matter, if you're finding them with that nice halo around them, even if you're not close to a stream, even if you don't have a really sticky, dense clay, that's pointing you towards the fact that that probably is seasonal high water table. So if you're getting all this data, you are near a stream, you are in an area that the web soil survey says should be wet, and you're seeing these soil morphology indicators of wetness. Put all those together, use your best judgment. That's a very strong indicator that indeed you do have a high water table. If only one or two is pointing towards it, that's where you get into that kind of gray zone where you start second guessing yourself, unfortunately. So again, relic colors here. And let's say you were finding colors like this, and you were digging in a soil, way up at the top of the hill. That would push me towards thinking that it's not seasonal high water table. But I would keep picking through the soil to see if I could find a root and look around that root and see if those gray colors form a sleeve around that root. Or is that root just running through red soil? And if it's running through red soil, I would say, yeah, we're up at the top of the hill. This should be a fairly well-drained soil. I've got a root running through. It's running through red pockets of soil and doesn't have a gray sleeve. I think this is relic color or lithochromic color. It's not indicative of seasonal high water table. If I was finding these same colors down at the bottom, though, that might be a little bit different. And of course, look at the soil survey as well, too. If I was finding this soil at the top of the hill in one of these blue areas, I'd probably say, no, I don't think this is an indicator of seasonal high water table. If I was finding this in one of these orange or yellow soils, which I know are colored that way because they are likely to have that high groundwater table, I'd be much more inclined to say this is indeed a sign of active seasonal high water. And there's a really good picture, again, from Dr. Galbraith, of a root passing through a soil. And you can see that real nice sleeve of gray colors right around it. So that means this root's being broken down and oxidized by bacteria, fungus, things like that. They're using up all of that available water, oxygen in the soil and creating that reduced conditions that's causing the iron oxide to dissolve and wash away. And then we've got that halo. In this case, it's a little hard to see the halo because it just looks yellow. But as you can see, we get, especially over here on this little lump, as we get further and further away from the root, the yellow starts transitioning into kind of an orange, and then compare it to the rest of the soil around, all those red colors. Obviously, this is still quite a bit lighter than those red colors over there. So you can really see that nice transition with that root going right through the middle. This is a perfect indicator of a redox model that is showing you do have seasonal high water table here. So hopefully you're not all more thoroughly confused than you were before. But I wanted to put my contact information up there in case any of you have questions that pop up later. Feel free to contact me. I don't have all the answers, but I will do my best to help and see if I can point you in the right direction.
Thank you, Dan. That was fantastic. Every time I get to hear someone speak about soils, number one, you can immediately see how passionate soil people are about soils, which is great. And I always learn something. So I want to provide some opportunity for questions. I did want to highlight a couple things. I took some notes because it was just so fantastic. So for everybody, I want to highlight what Dan said at the beginning of his talk. For these practices, VCAP practices that infiltrate water, we need to have at least a 2-foot separation between the bottom of the practice and that seasonal high water table so that they keep working. And Dan, you said, so we have happy participants. We want them to have a successful project. So that's number one. You also said you need to use your judgment. So this webinar was meant to empower you to use your judgment. Learn more, continue learning. We'll try to provide more opportunities. And this is empowering you to, again, protect your applicants, protect the people that reach out to you. But I want to be clear that it is not your sole responsibility to make this determination. As Dan said, it's tough sometimes. So this is also empowering you to be able to say, I'm not really sure. I think this could be a concern. We need to go to a professional to make a final determination. So make that clear. So without further ado, we've got a couple minutes left. If anyone has questions, I will pull up the chat. Or if you are so inclined, you can come off of mute and ask questions. Or maybe everyone's, I almost said percolating. That was probably a little too on the nose. Give you 1 more second. Oh, Emily, isn't that the question? Dan, I'm going to let you answer.
How accurate is web soil survey? It's a tough one to answer. I'd say as accurate as it can be. I think even a really good, well-made map, I forget there's a specific amount of the name soil that's supposed to be in each of those map units. So let's say, for instance, the map that I pulled up, a lot of those soils were Glen Elg, very common soil type around here. I think when you have a soil type that says it's just Glen Elg goes mapped here, you can be reasonably confident that 80% of that area is Glen Elg and 20% is something else. Now, usually that 20% is, fairly similar to Glen Elg, but sometimes it's not. Where you really get into some issues with accuracy is right at the border. We have to, for a map, put a border between one soil type and another, but one soil never perfectly ends right at another. It phases from one to another. So if you're at the border of a wet soil and a dry soil, that's when you're kind of a gray zone where you might find a little bit of both, or you might find a soil that has a water table directly between where you would expect to the two, the really wet soil down below you and the really dry soil above you. So maybe the wet soil down below has a water table at 10 inches, the dry soil above has a water table at 50 inches, and where you're standing right on the border of the two, you might find the water table at 30 inches. And that's not going to be shown in the web soil survey. So you do have to be careful when you get to those boundaries, because you got to put a nice, smooth, clear boundary on the maps, but really that boundary should be this wide, fuzzy line. And I would say too, especially in a county like mine, where there's a lot of urbanization, a lot of development, that tends to make it much harder to map soils, just because everything's gotten stirred around as well too. So I would say, if you kind of use the web soil survey as your first screening tool, and if you're going out to a site after you looked at the web soil survey and the web soil survey says it's a high dry soil and you're looking around and it looks high and dry, then I think you can be reasonably confident that the soil maps were correct. It's going to miss some of those small inclusions. So if you see a little drainage way, really small one going through this high dry soil, there's going to be wetter soil there, but it may not have ever been big enough to actually show on the soil maps. So yeah, I think, use it as your first point of analysis, but don't necessarily rely on it fully. It's always useful to go out and see the site as well too.
So I would also like to comment, I appreciate that, Dan. When it comes to creating an application, if web soil survey is saying this is going to potentially be a problem, it is then upon the applicant to prove it wrong. So we are going to err on the side of more conservative, but we want to open the door if someone is willing to spend the money up front to prove that that is not the case. Go forth and do so, and we will accept that application for review. That's a good question. So it is 3:01. So really grateful for everyone that came and got a little more knowledge. Very grateful to Dan for taking time. I know you are very busy. You've been working very hard out in the field for Northern Virginia. If you want to stay and talk to Rachel or myself and have any questions, we would love to chat. I'm going to very quickly put into the Zoom chat the information about the manual update webinar. You can register for it there. And I put some information about the water cooler chats as well. We will send a follow-up email after this training. So thank you guys so much and have a great rest of your day. And Rachel, you can stop the recording.